bulbs, we were able to get better output. You put the new bulbs together in combination with the reflectors, and we were able to get very quickly a 2x increase in cure speed, which was a good start, but still not enough. So the next approach then was to add thermal initiators, such as azo compounds or peroxides. This was problematic because of the chemistry of the components that were already there. We needed to actually heat one of the components up in order to get the thermal initiator to dissolve into it. And when you start adding heat and thermal initiators together, you can imagine immediately that you probably got a pretty unstable, unpredictable situation. And we found that happened a lot. A lot of cases, the components went off in the oven and such. The other thing we realized too was that this approach was going to be somewhat self-limiting, because you're taking advantage of the heat and the fact that you're underneath the lamps for a long time. Well, as you get going faster with your thermal initiator, that means you're spending less time under the lamp, and so your thermal initiator has less time to get kicked off. So you're going to very quickly going to be narrowing yourself down into a corner that's going to limit how much you can actually gain out of the whole thing. So in the end, we did see some results that were promising, but we were not able to ever consistently reproduce it. And the solutions are just too difficult to prepare. And this was on a lab scale when you're dealing with small quantities and it's an easily manageable situation. If you were in a factory and you had a large reactor where you're trying to do something like this, I just could imagine it being a huge nightmare. You have a whole reactor full of gel material that's just not going to drain out on it. So in the end, we decided to discontinue the thermal initiator. We can go strictly with the reformulation approach. So. Now, with the reformulation approach, there's two different monomers to consider. You've got the thiol, and you also have the ene. The review article that I mentioned earlier, the one by Coyle, actually has a couple of different lists in there that show what he's found over time to be the relative reactivity rate of the different monomers. In particular, he found that 3-alkyl mercaptopionates were the fastest, much faster than the alkyl thiols. The client in this case had already, not knowing about this review article, had actually lucked out or stumbled upon the fact, and they were using a tetrafunctional version of the 3 mercaptopionates. So in terms of the thiols, the literature said we can't do any better than where we're at. We're just going to stick with it. So we didn't try and do any substitution on the thiol side. On the ene side, though, there's also a similar type list. I only gave a partial portion of the list here, the parts that were most relevant to what we're talking about today. There were a few other exotic specimens that were more expensive that we never looked at, and the list actually goes quite a bit longer on the slower side. But, the ene that the customer had already decided on was a triol isocyanurate, shown here. That's number 3 on the list. So that means we still have the vinyl ethers and the allyl ethers as options. And notice too that the acrylates are listed as being actually slower than what was chosen up there. So this is the route that we proceeded to follow. Start first with the vinyl ethers. Before I get to that, I mentioned earlier that we were checking hardness with pencil hardness. I'm just going to briefly give you an overview of the test. There's an ASTM test for it, but basically you have a bunch of pencils all with defined hardness. There's a certain weight you put on the pencil and you drag it at a certain angle and you just look to see whether it scratches the surface or not. The scale is kind of a weird scale. I don't know how it got started. The hardness is 9H. These drop down numerically as you'd expect all the way to 1H. Then you get to an F, and then there's an HP, and then you get on the other side, and it's like with negative numbers, you're starting to go in the other direction from 1B all the way to 9. I don't have to necessarily understand all the details of it, but the big thing at least is to understand that a 9B is a lot softer than a 6B or such, and the opposite applies with hardness. The current coating, as I said, has a 4H hardness, so 4H and above, anything above 4H was considered acceptable in terms of hardness. So then looking at the monomers now, the first things we tried were the vinyl ethers. Those were the ones that were the fastest. Tried diethylene glycol divinyl ether. When we cured it at 90 centimeters a second, that's our target, that minimum speed that we had. We found HP, which is, remember from the previous slide, more or less is kind of like right in that middle range of the whole scale. Certainly well below 4H, and it dropped even down to 1B at a higher cure speed. We tried a triethylene glycol divinyl ether and found even lower numbers, 6p. Again, with the p's, the bigger the magnitude of the number, the softer it is. And also found similar results with the butane-diol divinyl ether. Now, one thing that we noticed with regards to this is that these are difunctional materials. They only have 2 ene groups on it, whereas they originally were using a trifunctional monomer. As a result, they were going to be much more, the original system we expected would have been much more tightly cross-linked, so it's maybe not that surprising that some of these values, even if it cured faster, didn't provide the hardness that was needed. The other thing you'll notice too, which isn't too surprising, but it's a well-known trend, but as you add more and more ethylene glycol monomers going from the di to the tri, you see softness. That oxygen bond in the middle allows the polymer chain to spin without any kind of steric hindrance at all, and so if you put any stress on it at all, whether it's from your hardness test or anything like that, it's able to very quickly and easily relax much more with the more ethylene glycols you add into it, the more you see that. So the next approach then was to try and find a trifunctional vinyl ether. We were able to locate only one, and you see we actually got good results. We thought we had got the big prize. 5H hardness at the minimum cure speed that they wanted, and even at 140 centimeters, 3 miles an hour, it still was an acceptable 4H. So that gave us a really good window. Problem is we handed this off to the client, and they came back very quickly and said the supplier is discontinuing the manufacturing of it, and that their anticipated volume that they were going to use of it wasn't going to be enough to keep the supplier to want to keep making it. So we had to go back and continue on. Next thing we tried was a allyl ether, which is shown here. This one also is trifunctional again because, as I said, we want to try and match the functionality of it. Unfortunately, this one didn't cure at all. We're not exactly sure as to why it is that it didn't cure. We tried a number of different options, different ratios of the thio-lene, and just never were able to get it to cure successfully. So then we finally succeeded in getting a breakthrough when we went to the acrylates. The first one up there is a triacrylate trifunctional, and that cured very fast, as you see here. It was able to cure at 90 centimeters a second, which the original formulation wasn't able to cure at. But we only had a 3H hardness, but it was a consistent 3H hardness, almost independent of speed. But when we went to the tetraacrylate, then suddenly we had the big breakthrough. Then we were able to get to 6H and 5H even at higher speeds. And feeling really good, we decided at one time to run it at 180 centimeters, 4 miles an hour, and we got 4H hardness. So now you're talking about something curing in 1/10 of a second. Going in at low liquid viscosity, 1/10 of a second later, it's completely cured, 4H hardness. That's pretty fascinating to watch. The other thing too is, if you remember back to the previous list, is that it did say that acrylates were supposed to cure slower than the allyl isocyanurates that were already being used. It turns out in this case, that's not true at all. The literature recommendation was wrong. So the lessons that we learned from all of this, again, is that higher functionality leads to higher coatings. That's really not anything new or revolutionary. Ethylene glycol groups also lead to softer coatings. Again, not anything too new. The monomer purity needs to be high in order to get these materials to react. And then lastly, that the acrylates can and do cure faster than the allyl isocyanurates, even if the literature is telling you otherwise. So in conclusion, we were able to finally reach an acceleration of factor of 20. The client wanted 10, we were able to give him 20, which made us feel really good. The final coating was actually even harder than what it was initially. It was at up to 6H instead of just being 4H, and we were able to retain all the other properties with it. And then, as I just finished mentioning, the literature rank in the acrylates is wrong. The other question we realized at the end of all of this, which we just raised, we didn't put the work into it since it's moot at this point. So we're wondering if we should have maybe gone back and looked at other thiols as well, because the thiol that we were using was the one that the literature said is the fastest, but this is the same literature that said that the acrylates would be slower than what had been used already. So maybe we should have gone back and looked at that too at the same time. Something for another day, another project.